All right, thank you. Hello, and welcome to the Corporate Sponsorship Senior Project Presentation. My name is Sloan Liu.
My name is Christopher Magot.
My name is Hui Huang.
My name is Aaron Wood.
And my name is Andy King, and we represent SlugSat.
So SlugSat is a multi-year senior design project where students apply their diverse engineering backgrounds in order to design and build a satellite from scratch. In the history of the Baskin School of Engineering, no team of students has ever been able to successfully launch a spacecraft. SlugSat hopes to change that by constructing and launching UCSC's first CubeSat. Success for us will pave the way for the Baskin School of Engineering to further aerospace opportunities for students, as well as provide more options for space and earth science research at UCSC.
For our first satellite, we have chosen to launch a CubeSat. Think of a CubeSat as a mini satellite. Numerous other universities have constructed CubeSats in the past, allowing us to conference with them for engineering advice if necessary, making the engineering process geared towards educating students on aerospace engineering. The CubeSat implementation is significantly cheaper in comparison to larger satellite model, and the NASA CubeSat Initiative program allows groups to launch educational CubeSats at a cheap cost by piggybacking on larger launch vehicles. Last year's team created a FlatSat, a flat version of a satellite, which met the minimum requirement for a satellite to operate in a controlled environment, as you can see in the slide right now. For this year's iteration of the project, we aim to create an engineering unit that will meet the CubeSat's requirements. We divided responsibilities according to the subsystems each team is working on. Each team member was responsible for a certain task, depending on their skill set and interest. The linear transponder is a mission payload that handles tasks critical to proceeding with our 2-year mission. The attitude control system ensures the craft maintains in the correct position during orbit. The onboard computer handles systems and data operation. The energy power system takes care of electricity generation, storage, and distribution. And the telemetry system is in charge of transferring data between the craft and the Earth. Lastly, as one of our missions in collaboration with the Santa Cruz Institute for Particle Physics, we introduced a science experiment subsystem, which was not included in last year's progress since they did not have the bandwidth to complete it.
This is a physical model of the satellite in its current form rendered using computer-aided design software. As you can see here, a CubeSat is a standard-sized satellite that fits in 1, 2, or 3 10 by 10 by 10 centimeter cubes. For this project, we choose to pursue a 2U CubeSat, meaning that our whole satellite is 10 by 10 by 22.7 centimeters. On the left is the outer chassis of SlugSat. The outside of the craft is covered in solar panels attached to the mainframe to help us generate power and also help us locate the direction of the sun. This is important for the attitude control system to know because it aids in pointing the craft in the correct direction. The slot on the top allows the antenna to deploy from its launch position. On the right shows a cutaway of the inside of the satellite. This shows how each system connects to each other. For example, the linear transponder needs to be close to the antenna to minimize transmission losses between amplifiers and the antenna. The radiation detector needs to be at the bottom of the craft because it needs to be face Earth in order to maximize the chances of detecting the radiation we are looking for.
Currently, our CubeSat has 2 mission payloads: the linear transponder and the low-energy radiation detector. The linear transponder benefits the ham radio community, but also serves as a backup means of communication in case of emergency or natural disaster when the internet or cell phone signals may fail. In addition to the linear transponder, the satellite will also carry a low-energy radiation detector designed to collect science data for the Santa Cruz Institute for Particle Physics. Specifically, it will detect radiation emitted during thunderstorm events called terrestrial gamma-ray flashes. This device will serve to further our understanding of thunderstorms and how they interact with our atmosphere. For further information on either of these payloads, please contact us using the information listed at the end of this presentation. The high-frequency linear transponder listens for and rebroadcasts radio signals in the 10 to 15 meter frequency band and extends the range of radio communications inside that frequency band. Last year completed a proof of concept linear transponder, which could theoretically work in space, but would not fit on our spacecraft. Our goals this year were to complete the boards that were missing from this proof of concept verify its space validity, and implement the space-grade components. After the completed SlugSat, we plan to integrate the linear transponder onto 2 circuit boards, which will follow the engineering unit standards set by the chassis subteam. However, due to the COVID-19 pandemic, we lost access to campus resources and were forced to work from home. For this reason, we instead studied the behavior of several of our building blocks in order to verify if their design meets our requirements. We also integrated the linear transponder on the engineering unit standard using computer-aided design software that allows us to turn an electrical schematic into a circuit board we can machine once the pandemic passes.
The low-energy radiation detector points at Earth and looks for low-energy X-rays emitting from the top of thunderstorms or the aurora borealis. This year, we worked closely with the Santa Cruz Institute for Particle Physics to design a system that converts the raw signals generated by the detector into a digital signal we can record into the craft memory and later downlink to mission control. We use a network of electrical circuits called comparators to detect different energy levels we can use to classify the radiation. The onboard computer then takes this information, gives it a timestamp, and counts how frequently the radiation bursts occur. We save this information in our large memory and send it to Mission Control in Santa Cruz next time we pass over this part of the world.
The Attitude Control System, or ACS, of the satellite is responsible for keeping our CubeSat in orbit and maintaining its orientation to fit our payload's needs. The main orientation requirement needed for our satellite is that it must be nadir pointing, which means the bottom of the satellite must be facing the Earth at all times during its orbit. The reason for this is because our science experiment must face the Earth at all times in order to collect data. The previous year's team was able to create algorithms to help our satellite reorient itself after launch and gave this year's team a solid foundation to build off of. So this year, our team was able to create a physical printed circuit board for the ACS. Here's the front side, and here's the back side. Our team also redesigned the propulsion system, which includes torquers. These sit on the top and bottom side of the board and move the satellite by pushing and pulling on the Earth's magnetic field in the X, Y, and Z directions. The propulsion system also includes reaction wheels. These are attached to the bottom side of the board and spin at varying speeds to control the spin of the craft using angular momentum. Our team this year was also able to correct a core problem residing in the software of the ACS, which relates to the previous year's decision of using solar panels for sensing the sun. Since the science experiment on board the craft must be pointed towards the Earth and be open to collect data, we cannot put a solar panel on that side of the satellite. This prohibits us from fully detecting where the sun is relative to our position. In order to solve this problem, the team decided to use a different method of sensing the sun, using light sensors instead. These sensors will be placed on all sides of the craft, providing our CubeSat with full awareness of the sun's positions at all times during the orbit.
The onboard computer of the SlugSat serves as the brain of the entire satellite. The onboard computer interacts with various systems of the craft to control its functionality and store critical data if necessary. Not only does it interact with all subsystems, it also establishes communication between the ground station and the satellite. The onboard computer also manages power consumption of the craft by turning on and off its systems when necessary. The onboard computer controls the following systems shown in the slide. This year, the team developed a fault-tolerant system on top of a distributed system to combat against transient memory issues that can happen in low Earth orbit due to radiation. The fault-tolerant system utilizes 3 CPUs to detect any software anomalies and fixes the software error. This essentially allows SlugSat to operate with error-free software while it's in its orbit.
Our team consists of a diverse group of 18 engineers peer-selected for their suitability to the project. In addition to possessing the core competencies that fit the needs of the project, SlugSat members are expected to adhere to the team effort mentality, yet possess the discipline to self-motivate and work by themselves if needed. A project of this scale naturally requires engineers with different educational backgrounds, and SlugSat's needs are no different. While electrical engineers make up the backbone of our team, we also employ the distinct skills of both computer and robotics engineers to accomplish some tasks electrical engineers may find difficult on their own. Through this method, we strive to create a collaborative environment where all members feel safe to express their ideas and everyone feels heard. We'd be lying to you if we said it was all sunshine and roses, but I can attest that beyond our professional relationship, we are all friends, and I hope to maintain contact with each of my teammates far beyond graduation.
Now, SlugSat as a project is also closely related to the UCSC Ham Radio Club, as well as the overall amateur radio community. Most of our team members are actually ham licensed, and about half of the team decided to become licensed after joining the project and understanding more about amateur radio. Here's a list of their call signs, which is a signature unique to each ham and serves as their identification when communicating with other radio operators. Being a ham also means potentially being one of the people to use our satellite's high-frequency transponder to communicate with other ham radio enthusiasts around the world. To raise the interest for aerospace engineering within UCSC through fundraising events and advertising amongst our friends, allowing us to take the first steps toward transforming our project into a club. This way, more students can get involved in the process of aerospace engineering and increase the chances of our satellite actually being launched.
By working closely with each other and the engineers who worked on previous years, we hope to have the satellite ready to launch by summer of 2023. Success will bring forth a new range of opportunities for students interested in aerospace engineering at UCSC and open the door for research opportunities relating to space. Thank you all for coming out today. If there are any further questions, we'd be happy to answer them now, or you can contact us at the information listed on this slide. Thank you.
Thank you.
Thank you.
Thank you.
Thank you, SlugSat, for providing a very welcoming environment for students to contribute to real and meaningful engineering.